2.2 Notes, Day 1, Polynomial Functions. In the last section, you learned about the basic characteristics of a monomial function. Monomial functions are the most basic polynomial functions. The sums and difference of monomials functions form other types of polynomial functions. Let n be a non-negative, so your integer cannot be negative, so you're not a rational expression here. And let a sub 0, a sub 1, a sub 2, and so on be real numbers with a sub n not equaling 0. The function given by the following thing. The degree is your greatest exponent. So you have to scan through and look for your greatest exponent. The leading coefficient is the variable with the greatest exponent. So you're looking for the greatest at both aspects. It says here we have a constant function and its degree would be 0. I'm having a hard time here. And then a linear function, its degree would be 1, and a quadratic function degree would be 2. Some characteristics of polynomials. Polynomials are defined and they're continuous for all real numbers, and they have smooth and rounded turns. So this would be an example over here. These would be non-examples. This right here is not continuous. It has a break. Even though the domain is, this would fill it on the domain, it still has a break on the graph. And this one right here has is not rounded. So without our calculator, we're going to graph these functions that we see on A and B. The big thing that we can notice is this guy's degree is 3, and I probably should put degree and not just D because you might think it's domain. So the degree is 3. It's a negative, that's one thing I want to notice. And I might rewrite it so that it's negative x to the third plus 4. So when I graph this, I know an x to the third power would normally graph going this way. The negative is going to flip it over the x-axis. And the plus 4 means we're going to go up 4. 1, 2, 3, 4. And you might have something that looks like that. B, we have g of x is equal to x squared, or the parentheses x squared, the quantity x plus 7 squared to the 4th power. I don't know why I keep saying squared. X plus 7 to the 4th power. That's the quantity. So in Algebra 2, you would have focused on the fact that this guy has a 0 at negative 7. 7. And the 4 would function pretty much like a parabola. The only thing is it's a little bit fatter or wider at the bottom, whereas a parabola might be just something like that. So those are the sketching those guys, and that's the end of that. So things that we're going to talk about today are leading term tests for polynomials and end behaviors. And you can use the degree and leading coefficient to determine the end behavior without having to graph it. If f of x is a polynomial of degree n and a leading coefficient of a to the n, then they follow these truths for end behavior. If n is odd, and a is positive, then you're going to have opposites end behavior. And the thing that I kind of remember is the linear function, like this. So as your x's are approaching negative infinity, your graph's going to negative infinity. As your x's are going to positive infinity, your graph's going to positive infinity. And that's when x is, or your coefficient is positive. When it's negative, it's just going to flip those. So it's just going to turn it in this direction. And you would go through the origin if it was just y equals x. I'm just sketching it, and of course my stylus isn't the perfect. But as you see right here, as my x's go to negative infinity, my graph goes to positive, and the reverse. As I go to negative or positive infinity, my graph goes to negative. Parabolas are even. Anything with an even exponent would be even, and they're going to have the same end behavior. If they're positive, they're both going to be going up. If it's negative, if the leading coefficient is negative, they're both going to be going down. For example, number 2, describe the end behavior of the graph of each of these polynomial functions using your limits. So first thing that you need to address is you need to figure out what the degree is. Once you figure out the degree, you're kind of halfway there. The leading degree, or the highest degree, is 5. So this is degree 5. Its leading coefficient is 4, and that is positive. So this is an odd function. This means that this guy's limit as x approaches positive infinity, the limit as x approaches negative infinity, that's a negative, is going to be opposite behavior. So I know this is just a sketch of this graph. I don't know perfectly, but I know that this graph is positive, so it's going to be doing this scenario. There's a lot of stuff happening in the middle, but I know that the end behavior would be such, where they're going opposite directions. So as I'm going to positive infinity, which is going to be this one, I'm going to positive infinity. As I'm going to negative infinity, my graph's going to negative infinity. Graph number 2. First thing, scan the problem, look for your degree. It looks like my degree is 6, so this is even. So this means I'm going to have both going in the same direction. My leading coefficient is a negative 2, and it's negative. So think about a parabola. When it's positive, it's going this direction. When it's negative, it's going that direction. So this graph is doing something like this. We know it's going down for both of them. So the limit as x approaches negative infinity, the limit as x approaches positive infinity, are both going to be going to negative infinity because this graph is going down. Zeros and turning point extrema. Zeros and turning points of polynomial functions. A polynomial function f of degree n greater than 1, greater than or equal to 1, has at most one distinct real zero and at most one or n minus 1 turning points. For example, if you have 3x to the 6th power minus 10x to the 4th power, 15 minus 15x to the 2nd power, then this has at most 6 distinct real zeros. And how they got 6 is because that's what this is. It's always going to have one less for the number of turning points. And by turning points, this would be a turning point, that's a turning point, and that's a turning point. So it's where you're turning your direction. So this one has actually, the graph suggests that it has 3 real zeros and 3 turning points. This is what at most it can have, is 6. It can't have any more than 6. So this is a general trend in your mind where you're thinking about what could be happening. Okay, so example 3, it says state the number of possible zeros and turning functions and then determine what the actual zeros are. So this is this guy's degree is 3. So that means he must have at least 3 real roots. And then it must have at least two turning points. Now when I actually factor, I notice right here that everybody has an x. So if I were to factor out an x, I would get x squared minus 6x minus 27. And that can factor to 9 and 3. I believe the 3 has to be positive. So this means that this guy has roots at x equaling 0, x equaling 9, and x equaling negative 3. In B, we have 4 real roots. We have at least 3 turning points because it's one less. And to factor this, at first I kind of looked at this and thought, uh-oh, how am I going to do an x to the 4th? But I notice right here that this, if I were to put an x squared in each of these, I think the 2 factors that multiply together give you positive 15 and add together to give you negative 8, and that would be 5 and 3. So x squared minus 3 equals 0 would be roots, and x squared minus 5 equals 0. So x squared equals 3 and x squared equals 5. And to undo those, I take the square root. When you take the square root, you have the positive and the negative values. So x would be plus or minus the square root of 5. Yep, got it in there. All right.